శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning, students. So in the last class we have discussed about the two applications of op-amp. So how op-amp is used as a summing amplifier. So in that class we have observed that the summing amplifier which can be created, that means in which we have used both inverting summing amplifier and non-inverting summing amplifier. If we give input to the inverting input terminal, then it is going to act as inverting summing amplifier. If we give input to the non-inverting terminal, then it is going to produce act as a non-inverting amplifier. So that's what you have observed in the last class. So you have observed about this adder using if you give for inverting terminal, if you give input, the output will be 180 degrees phase shift. That will be minus of V1 plus V2 you are going to obtain. And when you give, so this is what you have obtained in case of inverting summer. So in case of non-inverting summer, you are going to get the output which is equal to V1 plus V2 only. There will be no phase shift in case of non-inverting summing amplifier. And coming to the subtractor, so it is nothing but a difference amplifier. So as we know that the op-amp is nothing but a differential amplifier combination. So when we are considering op-amp as a difference amplifier, so then we are going to give the two input signals to the two inputs of operational amplifier, that is to the inverting input terminal as well as to the non-inverting input terminal. Okay, next in this class, so we are going to discuss about another applications of operational amplifier. So we will see. So here in this class we are going to discuss about differentiator, how op-amp is going to act as a differentiator. That means when you are going to consider this differentiator, so here we are going to show that the output voltage is proportional to the derivative of input voltage. So when we show this, then we can say that our operational amplifier can behave as a differentiator. For making, so this is differentiator, and then we are going to discuss about integrator, and then after the integrator, so we are going to discuss about the converter, which is going to convert the voltage which we have given into the current. So the change in the input voltage will result in a change in the output current. So this is what you are going to observe in voltage to current converter. And coming to next, current to voltage converter. So here in this circuit, we are going to convert the changes in the input current to the changes in the output voltage. So this is one of the application, and another application is, so how op amp is going to act as a logarithmic amplifier, and how this op amp is going to act as a anti-logarithmic amplifier. So logarithmic amplifier means output is natural log of input signal. Natural log of input signal, and anti-log amplifier, you are going to get input is a natural log of output voltage. So this is what we are going to observe in logarithmic amplifiers. First, we are going to discuss about the first circuit, that is differentiator. So differentiator is an electronic circuit, so which produce an output, which produces an output that is a derivative of input, that is a derivative of input signal. So coming to this, how we are going to construct this differentiator using our operational amplifier. We are going to observe now that how our operational amplifier is going to behave as a differentiator. For obtaining a differentiator, as you have studied in your, or you have been completed in your pulse and digital circuit subject, in linear wave shaping, there you have observed a differentiator using RC circuit. A differentiator using RC circuit. There, when you are going to apply the input signal to a capacitor, and when you are going to take the output across a resistor in RC circuit, then it is going to behave like a differentiator. Then it is going to behave like a differentiator. So the same circuit here we are going to implement such that here you can see a simple differentiator circuit. So in which input is directly fed to a capacitor C, and in the place of feedback resistor we are going to use a resistor R. So this circuit is going to act now as a differentiator. So here you can observe from this circuit diagram It is a simple differentiator and which input is given to the non-inverting terminal. So as we know that from the first class, from the class unit 3 starting onwards, we are going to observe that when we are giving input to inverting terminal, then the output, when we are giving input to the inverting terminal, then the output is nothing but 180 degrees out of phase with respect to the input signal. So this we have to keep in our mind, and then we are going to see the analysis part of this differentiator. So how it is going to produce the output signal, and how it is going to show the output which is a derivative of input signal. Here in this circuit, if you observe one thing, that is, if we have given input to the non-inverting terminal through a capacitor, and we have made the input is given to inverting terminal, and we have made the non-inverting terminal as grounded. So the non-inverting terminal potential is at 0 volts. So when it is grounded, we can say that the non-inverting terminal potential is at 0 volts. So when this potential is at 0 volts, according to virtual ground concept, according to virtual ground concept, so the potential at this node, that is the voltage at this node, will be 0. The voltage at this node will be 0. So as the voltage at this node is 0, then if you consider a nodal voltage equation, so then we can write a nodal voltage equation with respect to this node. So then here we are having a 0 potential. 0 minus Vi is the voltage drop across this capacitor, and 0 minus V0 is the voltage drop across this resistor, is equal to 0. So this is the Kirchhoff current law. So Kirchhoff current law. So by using that, so we are going to write the equation, and we are going to observe the output of this differentiator. So here you can see in this equation, you can see the capacitance C into derivative of. So what we have discussed is that the voltage drop across the capacitor is nothing but 0 minus input voltage. So that's what we have written here. Derivative of 0 minus input voltage. So 0 minus input will give nothing but minus input. So C minus C into dVi by dt. So see here. And then coming to another direction, so 0 minus V0 divided by R is equal to 0. So then we can write this equation like this: minus C dVi by dt is equal to V0 by R. So why we have written the d by dt of V? So here we are considering the voltage across the capacitor. So when we are considering voltage across the capacitor, that will be a derivative. So by this equation, so finally we have obtained that output voltage is equal to RC component into differentiation of input voltage. So if this RC value is equal to 1, if this RC value is equal to 1, let us assume like that, then the output is nothing but the derivative of input voltage. The output is nothing but the derivative of input voltage. So this is how the differentiator is going to produce the output as a derivative of the output voltage as a derivative of input voltage. And here the negative sign in the equation determines that there is a 180 degrees phase shift between output and input. So when we are going to observe the gain of for this differentiator, then the gain will be j omega into RC. So the gain will be omega into, so the gain will be omega into RC. So gain means V naught by VI. So which is equal to omega into RC. So then what happens? So when the gain is omega RC, so here when we observe the frequency response of this according to this factor omega RC, so omega RC results a frequency, so that frequency is going to disturb our differentiator circuit. So that is what the disturbance it is going to produce at high frequencies. Listen, at high frequencies the differentiator may become unstable, and this may lead to produce oscillations. So for that reason, so we are going to construct a differentiator. Such that, so we are going to place a resistor along with the capacitor, R along with the capacitor C, and we are giving input here VI. We are giving input here, and then we are making this non-inverting terminal to be grounded. And then what coming to this feedback, so already you know that the feedback is given with a resistor R. The same thing we are going to take here, and we are going to connect a capacitor in parallel with this resistor, so R. So let us assume as this as R1, C1, and this as feedback resistor RF, and this as CF. So this is the circuit we modified. So why we have modified this circuit? So generally the basic differentiator is going to produce oscillations at high frequencies. Instead of acting as a differentiator, it is going to produce some oscillations. So it is going to oscillate, nothing but it is going to oscillate at high frequencies. So for that reason, so for maintaining stability of this differentiator, so we are going to add this capacitor in parallel with the feedback resistor, and another resistor in series with the capacitor. So by adding these two, so the gain is going to become, so V naught divided by Vi is equal to what happens now. So if we consider this as impedance ZF, and if we consider this as impedance Z1, so then our V naught by Vi, our V naught by Vi becomes, that is the transfer function is going to become S into RF into C1 divided by, so 1 plus S into RF CF and 1 plus S into R1 C1. So the transfer function becomes like this. And then if we solve this, so by adding this, what happens? So the gain increases by 20 dB per decade. So the gain is going to increase at 20 dB per decade for a frequency f less than fb. So this improves nothing but the frequency response has been improved. The frequency response of this differentiator has been improved by adding this a resistor and capacitor. So that is why, so when we are going to consider practically, that means if you are going to do the experiment in our laboratory, then we are going to use this differentiator circuit instead of basic differentiator circuit, because basic differentiator circuit is lagging such that it is going to produce oscillations instead of acting as a differentiator. So we are going to use the practical differentiator circuit. So this is how the differentiator is going to produce the derivative of input signal as output. And the next circuit is integrator. Next we are going to discuss about the integrator. So what is this integrator and how it is going to perform integration? So here, in case of differentiator, as we know that in linear wave shaping you have studied about this integrator also. When we are going to take output across a capacitor and give input to a resistor, then the circuit is going to act as integrator. So the same thing here we have observed, and so in the feedback path we are going to connect the capacitor and here to the inverting terminal we are going to connect the resistor. So Vi is applied to the inverting input of operational amplifier, and V0 will be feedback through a capacitor C, and in place of feedback resistor here we are going to connect a capacitor. So then this op amp is going to act as integrator, and here you can observe that the non-inverting terminal of op amp which is grounded. So according to virtual ground concept, same thing. So we can say that the voltage at this node will be also 0. So by considering that if you write an equation, nodal equation, so at the inverting input terminal, so 0 minus Vi divided by R in that path, resistance in that path, and C into d by dt of 0 minus V0. So in feedback path, which is equal to 0. So by solving this equation, so you can observe here that dv0 by dt is equal to minus Vi by Rc. So if you bring Rc to the left hand side and d by dt to the right hand side, if you bring Rc to the left hand side and dt to the right hand side, so the equation will be like this. So now by integrating this equation with the respect to dt, so you can see integral dv0 is equal to integral Vi by Rc into dt. So now the derivative and integration will be cancelled on the left hand side, and coming to the right hand side, so as Rc is a constant value, you can bring out from the integration. So we have brought it out, and then minus 1 by Rc integral of Vi dt. So here from this equation you can observe, from this equation you can observe the output is integral of input. The output is integral of input, that is output is proportional to the integration of input signal. So that is how our operational amplifier is going to produce the integral as its output. So coming to transfer function, so if you observe the transfer function here,